Welcome to this thermodynamics subject and the fifth unit. So as per the JNTU Anantapuram syllabus, we are covering here. This is the fifth unit in the thermodynamics chart course or playlist, you can say. The topic is thermodynamic relations. We have to explain about thermodynamic. We have to explain about thermodynamic, thermodynamic relations. What is the thermodynamic relations? Generally, thermodynamic relations means what you are going to be relating with the pressure, volume, temperature. After that comes entropy, enthalpy, specific volume. Because Euler-Check we have started using from there, third you go to it. So then you will come here Maxwell's equations. The first one is the relation shown by this first scientist. Is what is the Maxwell's thermodynamic relation? So Maxwell's relations are a set of equations in the thermodynamics. So thermodynamics is we are heating with the heat which is moving in the dynamics form, which are derivable from the symmetry of second derivation and from the definitions of the thermodynamic potentials. So the derivations from the definitions of the thermodynamic potential. These relations are named for the 19th century physicist James Clerk Maxwell. This is the Maxwell. The four principal thermodynamic energies, their differential expressions and the corresponding Maxwell relations. So you are having four types of thermodynamic energy classifications. Here the differential expressions are there. Here corresponding Maxwell relations are there. Here you can see. So what is this? du ma is the internal energy, Gibbs law, and A is there. It is relation shown for this this one. Here also you are having I think Maxwell relation is there. The Gibbs relation is there. We can see here. So what they are dependent this unit one totally. This is the thermodynamic energies, different type of thermodynamics, internal energy. This enthalpy, this A means Maxwell's equation, Gibbs equation. So what is happening means internal energy is equal to temperature into ds. What is ds is difference between the two entropies, you can say, minus p into, so p means pressure into dv means difference in the volume. So here dh is equal to temperature into ds plus v into dp. If you are reversing this, you will get dh and dp. Only tds is common here, and you have to only, instead of minus you have to plus, and you have to reverse this equation, you will get this differential expression. Here also Maxwell, so dA is equal to minus s into dt minus p into dv. So this is just to replace this cds replaced in, and it is replaced by minus s into dt minus p dv. So Gibbs law also saying that same minus s means entropy into difference in the temperature, minus instead of minus plus, here we will come on dp. So it is very easy to remember. If you know internal energy, we can write these three equations here. So here also, if you are having my internal energy du is equal to, so what happens, this TDS is there, this is corresponding Maxwell relations or so natural derivations will be there. Here direct value was given. So this equation, so TDS here, a partial differential of temperature with respect to this volume is done. Here ds, which is constant here, kept up, which is equal to minus p into dv. So this dv is kept constant here. This partial equation of dp with ds is done here. So here also dp by dp and dt by dp, this s is just constant here. We can see this equation here is equal to dou v by dou s, p is kept constant here. So here also minus s into dou v, which is t is taken out, is equal to dou p by dou t. V is kept constant. But whatever the last term is there, that will be kept constant. So S is there. So d dou S by dou P is taken, and T is kept constant here. Here also same, V and P are there now. If remaining is temperature T. So dou V by dou T with P constant. So these are the equations of Maxwell's equations. So what is meant by TDS equations, you can tell. So the TDS equations, you can see here TDS equation, directly applying TDS equation to ideal gases. So TDS is equal to du plus PdV. So whatever the TDS is nothing but it is a heat ma. TDS means temperature into or difference in the DS entropy, which is internal energy plus P into dV work done ma. So internal energy and work done. So for ideal gas, if you are taking PV is equal to RT ma here. So what is happening is so this is a CV into T. CV into T is equal to DU divided by dt. We can do this way also now. So nothing but they have just a differentiated one. Differentiating, you get the equation. So this PV into RT, if you differentiate, you will get the constant this value. So here also you can see my it is given equally TDS is equal to du plus PdV. So this temperature T is coming down here, du by dt plus PdV by T ma. So which is PV is equal to RT ma for ideal gases. So what is happening? P by temperature T is equal to R by V. So this equation, you can see P by T is equal to P dV by T. So this are related and used for the problems here. So let us go for the definition. What is TDS equation enable us to calculate the change of entropy? What is the change of entropy? DS equal to S2 minus S1 or S1 minus S2 during various reversible process only, not irreversible process, only reversible in terms of either dV means volume, dt, temperature or dP. So these three temperatures you can see here. So either dV and dt. The first one is volume and temperature, or dP and dt. Two. Then third one, dV and dP. These are the relations we can get. And even in terms of direct measurable quantities such as coefficient of expansion and the bulk modulus. So you can also measure the bulk modulus by using this TDS equation. If I'm not wrong, I will take the third question. What is the difference in the specific heats now? So two types of specific heat exchange, that is constant pressure and constant volume. So here a specific heat set is the ratio of the amount of heat energy transferred to a object to any object to the resulting increases in its temperature. So what is happening ma? Energy is transferred to any object ma, and increase in its temperature. You are giving some heat to a object is continuously increasing. That is called a specific heat. The specific heat capacity is a measure of amount of heat necessary to raise the temperature of the 1 gram of a food substance by 1 degree. So you have to take 1 gram of salt or 1 gram of sugar or 1 gram of a water. Then you have to boil it. So how much of that taking one increase in the 1 degree of temperature. So that heat you are going to measure how much of heat you are giving. For example, if you take 1 gram of water and if you are continuously heating 1 calorie per grams centigrade, it is a one is coming here value. Silver 0.056 calories per gram temperature. Glass 0.20 calories per gram temperature. So these are the different specific heats given for water, silver, glass, oil, iron in the question. So if I'm not wrong, if I'm taking the next question here, what are the can see here what are the ratios of heat capacities. So what are the ratios of heat capacities is the next question. So generally, if you are taking here my definition, the ratio is generally given by the symbol gamma. So this gamma is equal to, this is the ratio of specific heat. So Cp into Cv is given by gamma, the product of constant pressure into constant gamma. Apart from any other reason, one reason for its important is that ratio is easier to measure preciously than either heat capacity separately. So ratios are very important one. So by ratio, two things are calculated very easily. For example, gamma is equal to Cp by Cp. So what is the value of Cp and what is the value of Cp means? So for monoatomic gases, so single atom gases, Cv is equal to 3 by 2. If you are taking this single 3 by 2 here, and keeping this in equation Cp is equal to Cv plus R. Here 3 by 2 times R plus R is equal to 5 by 2 times R. Therefore gamma is equal to Cp by Cv, where you can keep their 5 by 2 into R into 3 by 2, 2 cancels which is given by 5R by 3R, which is 1.67 is the gamma value of this one. So here, fifth question, if I am taking, what is the energy equations if you are taking? So the energy equations, expressions of the first law of thermodynamics or law of conservation of energy. So first law of thermodynamics says that whatever the energy is given, heat is given, is converted into internal energy plus work done. That is the law of conservation of energy. So the law is converted into some of the internal energy and external work. First, a balance equation for the rate of change of kinetic energy and internal energy is written. So sum is given for the kinetic energy, that is internal energy. The internal energy U may be related to specific heat at constant volume only. So internal energy you are getting means you are keeping the constant volume C. So here you can see from one side it is entering, the heat is entering into this cube, and from other side it is leaving here in the X direction, in the Y direction, in the Z direction also it is entering and leaving. So this is the dx, this is the dy and dz. So dx is there, dy is there, dz is there. From one side it will enter and one side it will be going out of this. So this is also here I am showing some pressure and volume. So this is actually I think this is this one I think a dual cycle or a dual cycle it is. So later I will discuss that one, that image. What is meant by Joule-Thomson coefficient? So Joule-Thomson coefficient, what is the explanation? So let us consider the Joule-Thomson coefficient. Here we are interested in how the temperature changes with the pressure in an experiment. So he has done an experiment with the how a temperature changes. He was very important about the temperature, which in which the enthalpy is a constant. The enthalpy he has kept is constant, only studying about different temperature. That is, we want to derive the Joule-Thomson coefficient mu is equal to dt by dou p. Sorry, so the coefficient, Joule-Thomson coefficient is given by dou T by dou P. So differentiation of temperature by pressure when enthalpy is kept to constant. Here you can see this is one side piston is compressing and other side also the piston is compressing. Here two temperatures we are having. So here this is P1, V1. Here one wall is made. This wall is this is having some air or liquid. You can say this air is pushed by piston. Then there is a high pressure, that is P1, V1. Here low pressures, this piston is putting on the air molecules, that is low pressure P2 and V1. So here, from here, what is happening? So it is kept low pressure area and high pressure area. So the formula is here given by coefficient dou T by dou P. What is meant by Clausius-Calparas equation? The seventh question it is, what is Clausius-Calparas equation? Any competitive exams also very important. So more generally, the Clausius-Calparas equation pertains to the relationship between the pressure and the temperature. Maximum in the AC unit, you can see that they have studied about only pressures and temperatures, or conditions of equilibrium between two phases. So two phases you want to study P1, V1 and P2, V2 of a object. So that is a Clausius-Calparas equation. Two phases would be vapor and a solid for sublimation, or a solid and liquid for melting. So one, you can go for sublimation process, means from vapor to solid. So this entry area at the vapor and exit area at the solid you will be testing. Or from solid, when you are burning the solid, you coming into liquid melting, that you can take here, the difference in the temperatures. So ln of P1 by P2 is equal to enthalpy by R constant is equal to 1 minus T2 minus T1. The difference between these temperatures, what making them is recorded here. So here, vapor and solid, some pressures are working, that is P1 by P2 are taken. Here, the temperature is taken. So this is the Calparas equation given here. You have to remember for competition. What is a Otto cycle? So the four-stroke Otto cycle is made up of the following four internal reversible process. So first one is 1 to 2. First isentropic compression is done. After that, volume heat addition is done. After that, it will burn because you're adding a heat into this Otto cycle. Then isentropic expansion will happen. So when expansion is happening, there is a work done. Work extension process is this. And after that, 4 to 1, the cooling process, that is a constant volume heat rejection is done in the Otto cycle. So here you can see this is the ideal Otto cycle. So this is what I'm telling 1 to 2. It is a first compression. Then what 1 to 2 is it is 1 to 2 is compression. Then heat addition, constant volume. Then heat expansion. Then heat rejection. So here heat is added. Here it is going out. Here compression is done. Here what expansion is there. 1 to 2 isentropic compression and 3 to 4 isentropic expansion. So isentropic. compression, expansion. These two are first and third one is similar. The second and fourth one is similar. 2 to 3, constant volume as combustion. 4 to 1, constant volume rejection. So what is the ninth question, ma? If I'm not wrong, what is a diesel engine? Simple diesel engine. You have to answer in only simple question. That is, what are the stages? How many stages are there? So diesel cycles have 4 stages: compression, combustion, expansion, and cool. Same, but here, see, ma, what is happening is, so this is the 1 to 2, ma, 2 to 3, 3 to 4, 4 to 1. So one is here constant pressure process, one is constant volume process, two are isentropic processes. So before that, you can see here, one is a constant volume, one is constant volume. This constant volume changed to constant pressure in the diesel cycle. So that is the difference between this diesel and Otto cycle, which you have to remember. So here, see, 1 to 2, it is isentropic compression. Here, 3 to 4, it is isentropic expansion, dead opposite. Then these two are opposite, constant pressure combustion and constant volume heat rejection. So at constant pressure, combustion is done, and constant volume heat rejection is done with the Otto cycle. So what is a dual cycle? So dual cycle is combination of two cycles, Otto cycle and diesel cycle. The dual cycle consists of following operations such as 1 to 2, it is isotropic compression. Then 2 to 3, addition of heat at the constant volume. Process 3 to 4, addition of heat at constant pressure is done. So here you can see, this is 1 to 2 is there. So isentropic process. 2 to 3, the constant volume. Here also constant volume. So this two constant volume, two isentropic process, it is a Otto cycle. When this constant pressure process is added, for two isentropic process, one constant pressure, one constant volume, it is diesel cycle. So combination of petrol and diesel giving you this picture. So you have to, that is a dual cycle. So just a last question, I think it is a comparison you can do beautifully between Otto, dual and diesel cycle in the form of heat. So the main difference of Otto, diesel and dual cycles depends on the thermodynamic process. Concerned, how about add heat, where you are going to add heat? The areas are very, very important. You can see the diagram also. In the Otto cycle, heat addition is isochoric. Heat is added to the engine when the piston is at the top dead center. So when the piston is at the top dead center, the dual cycle is a constant pressure and a constant volume heat addition cycle. So in the diesel cycle, what happened? Constant pressure and constant volume is there. So here you can see, this is the first one. Where is this? This is the Otto cycle. What is the Otto cycle is telling is, so heat is addited at constant volume, heat rejected at a constant volume. So that is a high isochoric. The heat addition is isochoric. This is the heat addition. Isochoric here. The dual cycle constant pressure. So this is a constant pressure in the dual cycle. What heat addition is there? At constant volume, heat is rejected. So this is the one in dual cycle he is showing. So dual cycle here, sorry, this is a dual cycle. What is happening? Constant pressure. This is the constant pressure, constant volume. Heat added and heat is rejected here. Both things at constant volume and constant pressure, both things heat is added. So more heat is available in the dual cycle. So that is the Otto cycle has the highest work output and efficiency. Who is having more efficiency? Dual cycle, diesel cycle. This one means. So obviously, work output is more for Otto cycle. That is this middle one only, and more efficiency also for this only. Diesel cycle has the least efficiency. So diesel cycle is having a very very less efficiency. So first is coming Otto, second is coming dual, and third one is coming diesel. The dual cycle has the efficiency between Otto and diesel cycle. So what is the efficiency of this diesel cycle is in between this Otto and diesel dual is coming. Okay, same as the same compression ratios and the heat addition is there. So when same compression ratios and heat addition is there. With this, I'm completing this EDS. I have covered all the 10 to 11 important questions in this unit, which are very useful for you. I think you will understand with minimum basics in this condition. Any questions or any queries or any suggestions, please give me. I will update in the next video. Thank you, ma. Thank you, Ashwin, for this.